Good morning, everybody. So, we will continue with our previous topic, and we will today what we will do can be termed as ebullition from hot surfaces. Now, as we have seen that in case of boiling heat transfer, heterogeneous nucleation is very important, because most of the practical situation we have got heterogeneous nucleation, and that is from a surface which is being heated. So, basically from that hot surface the heat is being transferred to the liquid, and the mechanism is predominantly evaporation. Now, in the solid surface, as I have told that there are number of pits and cavities. On these pits and cavities, some vapor nucleus that is formed, and that grows as a as a bubble embryo bubble, and then it becomes bigger and bigger. Now, obviously, a bubble which becomes bigger and bigger, that cannot go on growing continuously, infinitely it cannot grow. So, it has to grow, come up to certain size, and then it will leave the surface. Then again a new bubble will grow. So, this cycle is known as ebullition. So, ebullition what we are going to study today is this cycle. Now, you see, the first thing which we have to remember is that the process of bubble growth and collapse that is transient. Obviously, there is a change with time, and also this process is intermittent. Okay. So, this process is intermittent, and then it starts with nucleation. Process starts with nucleation. So, in this connection, in our last class we have described the heterogeneous nucleation, and we have shown or discussed that the cavities in a solid surface that can be idealized as a conical hole. So, this is some sort of a conical hole, and this has got a temperature T wall. This hole, though I have shown it in an exaggerated manner, but it is very small, and it is embedded in the solid surface itself, whose temperature is T wall, and somewhere away from the wall we have got a temperature of the fluid that is equal to T infinity away from the wall. Now, here as I have told that these pores, they may have some amount of vapor in it, or they may have some amount of permanent gas. So, initially we will have some meniscus over here like this, and one can see this is the angle. So, this is the angle one can see. Now, what happens on a flat surface when boiling is taking place? We can have some sort of a contact angle, or for that matter on the flat surface if there is a bubble, we can have a contact angle, and that contact angle is called theta. So, this can have some sort of a contact angle, and that contact angle can be called as theta or can be termed as theta. In this, what is happening, that we can measure the contact angle the way I have shown, or we can measure the contact angle with respect to the flat surface itself. So, if we measure the contact angle with respect to the flat surface, then we call this angle, or then we refer this angle as theta dashed, and theta dashed is called the apparent contact angle. So, theta dash, if we do little bit of analysis, suppose this is our cavity which is having an included angle of beta. This cavity is having an included angle of beta, and let us say the for the solid liquid pair the actual contact angle is theta. So, theta is the actual contact angle. Then we have got theta dashed, that is the apparent contact angle. So, obviously, theta and theta dash, they are related through beta. The relationship will be theta dashed is equal to theta plus 180 degree minus beta by 2. All the angles are measured in degree. Now, you see this relationship, it gives a very unique situation, it can give rise to a very unique situation, that sometimes this theta dash can be even more than 180 degree. Okay. Depending on the value of beta, the theta dash could be more than 180 degree, and smaller the value of theta, smaller the value of beta, that is the included angle of the conical pore, the possibility of theta dash becoming more than 180 degree, that increases. In other words, one can tell that apparent contact angle will increase as the included angle of the conical pore, that decreases. So, what does it give? That if theta dash become more than 180 degree, then what does it give? So, this is giving a very unique situation. So, if theta dash become more than 180 degree, then we get we have told that delta G is the energy required for a vapor nucleus or a bubble nucleus to form. Now, delta G will become negative if theta dashed becomes greater than 180 degree. Physically, what does it mean? Physically, it means that even without any degree of superheat, even when the liquid is not saturated, a negative superheat, there could be formation of vapor bubble. Now, actual situation is not so. There is another physical interpretation, that suppose we have got this kind of an interface, the theta dash is becoming 180 degree, that can be related to the, here we have got vapor or you can have permanent gas, or you can have a mixture, and here you are having liquid. So, here you are having liquid. So, it also means the liquid pressure is more than the pressure of the permanent gas or the mixture of vapor and permanent gas. So, physical meaning one can get, but really will there be any evaporation if there is theta dash greater than 180 degree. So, that we have to see and for that we have to analyze or closely observe the process of vapor nucleation at a particular site of nucleation or at a particular pore site. Now, there may be several possibilities. Let us examine the possibilities one by one. See, as I have told, some amount of vapor or gas or a mixture of vapor and gas that is entrapped over here, and this angle is beta. Now, if this angle beta is very small, very small, then what will happen? Whatever gas or vapor that is entrapped, and for the vaporization process we need some amount of heating. So, that gas or vapor may diffuse in the crack or in the pore itself. As the temperature is increasing, the diffusion coefficient will also increase, and then the small amount of vapor or gas that may also diffuse. Then what will happen? It will not act as the nucleation site. Now, other thing can happen. Suppose we have got initial interface like this, meniscus like this. So, this will, due to heat transfer, this will grow. This can grow by different process. The gas can expand or there could be additional evaporation, the volume is increasing. So, this meniscus will go up and up. So, what one can have? One can have, this is location 1, this is location 2, this we can have a location 3, something like that, very close 3. Then one can have something like that 4, one can have 5, this is 4, this is 5, and also in some cases it can come out of the vapor cavity, sorry, the surface cavity, and this we represent as 6. And when we are doing this, how we are getting this? We are getting this with the increase of temperature. With the increase of temperature means which temperature is increasing? The solid wall temperature is increasing. Liquid temperature is more or less kept constant. So, if the liquid temperature is more or less kept constant and solid wall temperature that is increasing. So, what will happen? In an essence, the degree of superheat that is going on increasing. So, if I make a plot, I will have this kind of a phenomena. This side is bubble volume, which is going on increasing. So, really it cannot be called a bubble volume, but it is the volume of the bubble embryo. So, this is going on increasing, and then delta T sat, which is proportional to 1 by r, that is plotted in the, or that is in the other coordinate. So, what we will have? We will have a figure like this. So, 1, there is no change of angle. 2 also, that is a flat interface, there is no change of angle. Probably 3 is very close to 4, there is a change of angle, slight change of angle. Then we have got 4, then we have got 5, and then we have got 6. So, 1, 2, 3, 4, 5, 6. So, these are at different position, how there is a change in the radius of curvature, 1 by r, actually it is the radius of curvature, how there is a change in bubble volume, and what is the corresponding delta T sat that we are getting from this particular curve. Now, here we can see that the curve has got a peak. So, this value is called critical value of superheat. So, basically this is good enough for the bubble to grow further, and ultimately this is good enough for the bubble to leave the pore or the cavity. Okay. So, this is what we will have in the actual practice of boiling. So, you see though the included angle beta is important, another important thing is coming, which is the radius at the mouth of the bubble, because you see it is connected to the bubble volume 5, which is just at the mouth of the pore, and it has got this bubble radius, it has got some sort of a relationship with the radius of the pore mouth. Okay. So, people have done lot of mathematics, so you will not go into this, but let us keep our physics clear, that when a bubble nucleation will take place from this pore, this included angle is important, and at the same time the radius of the bubble mouth, that is also important. Now, with this additional thing, which is just an extension of our of the previous topics which we have learned. So, now we go to the evolution cycle of a bubble. Now, evolution cycle of a bubble, that means the cycle of bubble growth and bubble collapse, as I have already told you, that it means the growth and collapse of a bubble. Now, it has got separate, I mean different stages. Now, different stages, if we see, we have to make some sort of idealization, and based on this idealization we will make a phenomenological picture of what is happening at a hot surface. So, what is happening at a hot surface is like this. At the hot surface, let us say the surface is kept at a temperature T wall, which is greater than T saturated. Unless this condition is met, we will not have boiling. Now, the dotted line what I have drawn, though one may think that the bulk of the liquid will be at saturation temperature, but very near the wall, as the wall temperature is higher than the saturation temperature, it could be substantially higher even. So, very near the wall, there is some sort of a temperature continuity between the solid phase and liquid phase. So, we will have the liquid layer at a temperature more than the saturation temperature. Basically, we will have a thermal boundary layer. So, the broken line whatever I have drawn, that is called edge of the thermal boundary layer. Edge of the thermal boundary layer we are getting. And again, to keep things simple, what has been done, that it has been assumed that the temperature changes here linearly, and this one we can represent by delta T, that is the thickness of the thermal boundary layer. So, basically we have got our y coordinate in this direction. Now, if I see different dimensions of the bubble, we have got y here from the top of the bubble, and then we have got 2 r e, r sub e. So, what we are calling this not as a fully formed bubble, fully developed bubble, but it is some sort of bubble embryo. So, to mention that it is embryo, this suffix e has been brought here. So, 2 r e is the bubble diameter, or the diameter of the bubble where it is, I mean where we have taken the diameter where it is the largest, it is having the largest value. So, here 2-3 parameters are important. This is also denoted by people as B, the height of the bubble, that is also denoted as B. So, y is equal to b, that is equal to approximately twice R c. What is R c? R c is the cavity radius at the mouth of the cavity, and by some analysis and observation people have also got it as equal to 1.6 R e, where e is the radius of the bubble embryo. Okay. So, this is the picture which we want to have before we go further for analyzing this particular situation physically, and then some amount of mathematics we want to discuss in connection with this bubble nucleation process. So, if we see these steps by which the phenomena is occurring, initially a small embryo exists at the cavity. Initially, this will exist at the cavity, and as I have again talked earlier, this embryo could be this embryo could be vapor, this embryo could be a mixture of vapor plus the permanent gas. Basically, what people have argued and also seen by from experiments, it is like this, that presence of permanent gas is very, very important. Okay. And for the creation of the vapor nucleus, at least a few molecule of the permanent gas is needed initially. So, the bubble is presumably formed. How it is formed? So, presumably the bubble is formed from the residual part of the previous bubble. So, this is how this bubble is formed. So, initially there was, or previously there was another bubble. So, from the residual part of this vapor nucleus or the bubble is formed. The now, what I have assumed? I have assumed that the wall is covered with, here it is T infinity, here we have got liquid, with high temperature. Now, when a bubble will leave this surface, so what will happen? Let us say this bubble is leaving this surface. So, when this bubble will leave this surface, along with it, it will also take the heated up liquid. So, let us say this is a particular cell, when the bubble is leaving. So, it is not leaving without any liquid, it is taking this cell along with it. Okay. So, this is also another assumption which is made, that when this bubble leaves, it will leave with certain amount of liquid surrounding this, and this is a common phenomena, it will happen. Now, if it leaves then with some surrounding liquid, then a very simplified mechanical or mechanistic representation of the process will be something. So, this is the hot surface, up to this we have got heated liquid, up to this we have got heated liquid. This place cannot remain vacant. So, this will be filled up by colder liquid. So, this will be filled up by colder liquid. By surrounding colder liquid or from the top, the colder liquid will come and fill up this place. This is a very simplistic representation of the process. Now, again if a bubble has to grow, then what will happen? This place has to be filled up, or this place the liquid has to gain a higher temperature, otherwise the bubble growth will not take place. So, now up to second stage I have written, third stage will be transient heat transfer. So, that the colder liquid is heated. So, there will be transient heat transfer and the colder liquid will be heated. Now, so for this heating process what will happen? A finite time will be needed. So, a finite time is needed for this heating process. For this heating process a finite time is needed, because it is a heat transfer process, it is some sort of a transport phenomena, instantaneously it cannot take place. Now, this time duration is known as waiting period. So, this time duration is known as waiting period. So, in the evolution cycle or bubble growth cycle, the first time duration what we get is known as the waiting period, and people have also estimated what is the time needed for this waiting period. So, this is denoted by T w. This waiting period is also denoted by T w. Another postulation is made. Another postulation what is made, next point, that this is the edge of the boundary layer. Above this there could be strong convection and turbulence, but within the thermal boundary layer the heat transfer within delta T, heat transfer is by diffusion, molecular diffusion. So, this is also another postulation which has been made, that within the thermal boundary layer the process is by molecular diffusion. So, basically then we are having two region when delta is y is greater than equal to delta T. So, we have got the effect of turbulence, and y less than equal to delta T, we have got molecular diffusion, transient conduction is the attribute of that. Okay. Now, we can proceed for some sort of analysis. Another thing what has been postulated by people, that basically the conduction is along one direction. What is that direction? this is along the y direction, okay, because heat is being transported in that direction. So, we have got one dimensional transient conduction, and if we define theta that is equal to T minus T infinity, assuming that the bulk temperature more or less remains constant. So, the equation which we will get, that is d theta dt, that is equal to alpha L d 2 theta d y 2. So, this is our transient one dimensional conduction equation which we will get. What are the boundary condition? Theta is equal to 0 at T is equal to 0. That is, just one bubble have left and that place has been replaced, or that vacuum place has been replaced by colder liquid from the top, and the colder liquid is having a temperature of T infinity. So, that is why the non-dimensional temperature will be 0. For theta greater than 0, what we will get? Theta is equal to theta w, that means it is T w minus T infinity at y is equal to 0, and theta is again equal to 0 at y is equal to delta t at the edge of the boundary layer. So, these are the boundary conditions we will get for this particular equation, and we can see that it is what? It is a equation involving both t and y. First derivative of t is involved and second derivative with respect to y is involved. First derivative with respect to t and second derivative with respect to y. So, accordingly we have to have the boundary conditions. Now, this type of equation is very known kind of equation what you have done in your heat conduction or heat transfer. So, what will be the solution? There could be different methods of solution, but one can get the solution by separation of variable. There could be other method, but by separation of variable also one can get the solution. So, if we see any standard reference, so it will be theta by theta w, that is equal to delta t minus y by delta t plus 2 by pi summation n is equal to 1 to infinity cos of n pi by n sine of n pi delta t minus y by delta t e to the power minus n square pi square alpha L t by delta t square. So, this will be the equation. Obviously, you can see that up to this it is taking care of the spatial variation with space, and the exponential term that is taking care of the variation with time. How does this curve look? If we have some sort of a non-dimensional plot, the curve look like this. We have got y by delta t, this is 1, and we have got this side as t minus t infinity by t wall minus t infinity, this is also 1. So, in steady state it will have some sort of a linear profile, but otherwise it will have profiles like this, and in this direction you have got increase in time, time is increasing in this direction. So, we will have a temperature variation inside the thermal boundary layer in this particular form. All right. Now, what we can do, is that we are already familiar with this particular form of equation, that delta T sat, that is equal to 2 sigma T sat by rho v H L v R e. R e is the radius of the vapor embryo. Now, here we will replace vapor embryo, we can replace vapor embryo by the radius at the mouth of the conical pore, and the relationship which has been suggested for the dimensions of the vapor embryo at the cavity mouth. What has been suggested? Already we have mentioned that B is equal to twice R C is equal to 1.6 R E. This relationship has been suggested. So, if I use this relationship and well, the previous relationship of delta T sat also if we use, and we can make further simplification. So, one get theta sat by theta w is equal to 3.2 sigma T sat by theta w rho v H L v delta t, and here delta t by y. Sorry, I have made a mistake. So, this plus this is equal to your theta L E by theta w. So, this kind of a temperature profile we can get by incorporating the very well known equation which relates the change in or rather the degree of superheat with the vapor embryo nucleus. Now, here theta L E is the temperature at the edge of the boundary layer, liquid temperature at the edge of the boundary layer, theta W is the temperature at the wall. Okay. Now, if the site is to be active site, if the nucleation site is to be active site, then for the site to be active, theta by theta w, that should be theta L E by theta w. Obvious, this is not a very great thing. What we are telling that you have to remember our earlier phenomenological explanation, that this is your T L E or T infinity. Now, if the site has to be active, then what has to be there, that here after the bubble have departed, we have got a temperature which is lower compared to the wall temperature, but that could not be too low, and here we should have a higher temperature liquid. This should be replenished by a higher temperature liquid. So, that is what has been told. Now, now, if the bubble has to really grow, then what will happen, that we can also write theta by theta w at y by delta t, that means within the boundary layer, the maximum value with respect to the bubble, it could be B by delta T, because the bubble height I have represented by B. So, this B is again related to twice R C by delta T, that should exceeds, it should exceed theta L E by theta W. So, this is what I like to tell. That means, when the bubble is growing, bubble embryo is growing, you have got even the topmost portion of the bubble embryo submerged within a high temperature liquid. Okay. So, the maximum point which can touch the edge of the thermal boundary layer is this. So, this point can touch the, at least at the limiting process, it can touch the outer edge of the thermal boundary layer, and that has been put in the mathematical term in this particular equation. Okay. Or in other words, the vapor embryo can grow only when it is wholly surrounded by your superheated liquid, by a hot liquid. Why? Why that is needed? It is needed because once it comes out of this cavity, once it blossoms outside, then the growth is possible only by further evaporation. Further evaporation will be possible if this temperature is higher. Now, at some part, let us say this temperature is higher, further evaporation is taking place, but at some part this temperature is not higher, then a condensation may take place. So, we will not get an effective growth of the vapor embryo. So, that is why it is postulated that the entire, for the growth to be effective, the entire of the bubble should be submerged in a high temperature liquid pool. That is what mathematically has been put. Now, this side is your T minus T infinity by T wall minus T infinity, this side is your y by delta T, and we are drawing the temperature profile within the thermal boundary layer. So, this is the linear temperature profile at the steady state. Over this, if we, and this is the linear temperature of the thermal boundary layer in the steady state, means all the other temperature profiles are below this. So, maximum value which can be reached for the temperature within this thermal boundary layer is given by this particular straight line. Other lines are like this. Okay. Now, what we do, the delta T sat equation, what we have written already for the vapor bubble, suppose this equation which we have written for the vapor bubble, this equation if I superimpose on this curve. So, what I will find that this equation is cutting the steady state temperature curve at 2 points. Okay. So, if it is cutting or intersecting the steady state temperature at 2 different points, so these two superheat values are very important. So, these two are the limiting superheat values. Okay. And corresponding to these values, we can also calculate, already those equations has been given to you, what is the nucleus, vapor nucleus radius, that also we can calculate. Those equation has already been given to you in our previous class. So, what we can get, that suppose the vapor nucleus, corresponding vapor nucleus, that is given by R c. So, we will have a situation 2 R c by delta T, there will be a maximum value, this is a typical value of the vapor nucleus and this is your 2 R C. Actually, this is minimum, sorry, this is minimum delta T maximum. That means, what is R C? R C is the radius at the cavity mouth. So, that cavity mouth radius we can get from this equation that it can have a maximum value, it can have a minimum value. If some value is more than the maximum value, then it is not operative. If some value is less than the minimum value, then also it is not operative. And any value in between this will be a cavity which will be operative and which will give us the vapor nucleation. So, that is the information we can get from here. Now, another thing we can do, we can calculate, let me write it here, R C min and R C max we will have this one. Delta T by 4 within bracket 1 minus theta sat by theta w. This is plus, this is minus, one minus theta sat by theta w whole square minus, this is within the square root itself, 12.8 sigma T sat by rho v H L v delta T and theta w. So, this is within the square root. So, let me put the square root over here. So, you see from this equation R C min corresponds to the plus value, R C max corresponds to the minus value. Okay. So, within this values we will get the R C minimum and R C maximum. Basically, R C minimum and R C maximum, if we see that it depends on number of fluid properties. It depends on sigma, it depends on rho v, it depends on HLV, etc. So, it depends on a number of fluid properties. It also depends on delta T, the thickness of the thermal boundary layer. Okay. And wall temperature, this could be a variable one, but it also depends on the theta saturation temperature. So, now we can plot curve, how does this curve look for different fluid under different operating condition. Let us consider that we are having water and under atmospheric pressure and we have estimated delta T is equal to 0.2 millimeter. Now, this side is your R C, okay, and this is a semi-log curve. So, we have got 0.01, then we have got 0.1. Okay. So, these are different dimensions and this side you have got these dimensions are in millimeter and this side we have got T w minus T sat. So, degree of superheat. So, 0, we have got 2, 4, 6, 8 like that we have got. So, the curve which we will have is something like this. So, what does it mean? This means that this is the range of active cavities. So, active cavity, it will depend on the fluid and delta T as I have told, but it will also depend on T W minus T sat, that means the degree of superheat. So, at this degree of superheat, let us say at this degree of superheat, only the cavity pore size or pore radius, because I have pore radius at the mouth I have taken. So, that is the value of R c. So, only these cavities will be activated. So, this curve is flaring out. So, you will have higher degree of superheat. So, a larger number of cavities will be activated. So, that is why we get, as we have, I mean we can relate it to our day to day experience, that as we increase the temperature, let us say on a container boiling is taking place, as we increase the temperature we see more vapor bubble formation, because the more number of cavities are getting activated. Now, what happens this side and this side? See, below this it is very easier to tell. So, below this what will happen, that it will not, I mean this cavity is so small that it is not activated and it will not act as a bubble nucleation site. Above this what is happening? See, this line is more or less a straight line, this line is flaring. Above this what is happening? Above this the cavity, I mean the vapor bubble does not identify it as a cavity, it is identified as if it is a flat surface. Okay. So, this is how your vapor nucleation is taking place and range of active cavities are increasing. But what I like to tell you, that these calculation you can also appreciate that these calculations, these analysis has been done based on a large number of assumptions, very simplified model, only to give some overview of the physics what can happen, this model has been proposed. So, actual practice there could be lot of differences. In actual practice, the process of vapor nucleation from a small cavity could be a physico-chemical process also. What I mean to say? Suppose there is a very hot surface and we are looking into the boiling process in a liquid metal. So, what will happen? The liquid metal may have some reaction with the hot surface, some oxide formation could be there, or with some previous oxide layer it can have some reaction. So, it could be a physico-chemical process also. So, based on very simplified approaches and assumptions, this has been described, more or less the physics is like this. Okay. But obviously, the model has got lot of loopholes, even then it can justify whatever is observed experimentally quite well. So, I think I will stop here, next day from this point we will start again.